Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Emile Borel's 1909 paper, Les probabilites denombrables et leurs applications arithmetiques, stands as a monumental work of synthesis, a document that forged a profound and permanent link between the developing language of probability and the ancient certainties of number theory. It presented to the world a new way of reasoning about the infinite, one that could deploy the logic of chance to uncover deterministic truths about the very fabric of the real number line. This essay undertakes a direct and systematic evaluation of the paper's internal claims, proceeding section by section to analyze the specific arguments, mechanisms, and conclusions that Borel constructed. We will explore the logical architecture of his probabilistic innovations and assess the power of their application to the arithmetical properties of real numbers, revealing the work as a masterclass in conceptual engineering and a foundational text for 20th century mathematics. The analysis will focus entirely on the content and logical structure of Borel's own presentation, evaluating the coherence and significance of the claims as he laid them. Before the academic, Section 1, the principle of total probability. For a denumerable infinity of events, Borel commences his argument by positing a crucial extension to the classical theory of probability. He addresses the scenario of a denumerable, or countably infinite, sequence of mutually exclusive events. The core claim of this initial section is that the principle of total probability, which for a finite set of events dictates with their probabilities, summed to the probability of their union, can be extended to such a countable set. He asserts that the sum of the probabilities of a countably infinite collection of disjoint events is equal to the probability that one of them occurs. A direct consequence of this, which he implicitly accepts as axiomatic, this total sum must be less than or equal to. This assertion represents a profound conceptual leap. Classical probability theory, rooted in finite sample spaces and combinatorial calculations, possessed a firm foundation for finite additivity. Borel's claim moves the discipline into the realm of the infinite. He presents this extension with the confidence of a self-evident truth, a necessary axiom for any meaningful discussion of infinite sequences of chance occurrences. The evaluation of this claim reveals its foundational character. Without this principle of countable additivity, the entire intellectual edifice of the paper would be unstable. It is the bedrock upon which all subsequent arguments are built, allowing him to treat infinite series of probabilities as coherent mathematical objects that correspond to meaningful probabilistic statements. The mechanism is one of generalization by fiat, a bold stroke that redefines the scope of the field and prepares the ground for a theory of measure. Section 2, the criterion of infinitely repeated trials, and the concept of zero probability, events building upon the foundation of countable additivity. Borel introduces his first major analytical tool, a powerful criterion for assessing the likelihood of events that occur infinitely often within a sequence. This argument, now widely recognized as the first Borel-Cantelli lemma, forwards a specific and potent claim. It states that if the sum of the probabilities of a sequence of events, say event 1, event 2, and so on, constitutes a convergent series, meaning its sum is a finite value, then the probability that an infinite number of these events will occur is precisely zero. The internal logic of his proof is elegant in its construction. He considers the probability of at least one event occurring after the nth trial, and shows that this probability must approach zero as n tends to infinity, a direct consequence of the series of probabilities being convergent. From this, he concludes that the event of infinitely many occurrences, which would necessitate occurrences for arbitrarily large n, must have a zero probability. The evaluation of this claim shows its immense utility for the paper's ultimate goal. It provides a rigorous method for dismissing certain outcomes in an infinite process as, for all practical purposes, impossible. Borel is making a subtle and deep argument about the meaning of probability 1 and probability 0 in an infinite context. He equates a probability of 0 with a form of practical impossibility, allowing him to filter the set of all possible outcomes, isolating a subset of negligible or exceptional cases. This tool transforms an abstract probabilistic sum into a definitive statement about the long-term behavior of a system. Section 3. The construction of the probability space on the unit interval. The paper then transitions from abstract probabilistic principles to their concrete instantiation within the domain of arithmetic. Borel's central claim in this part of his work is that the selection of a real number from the interval between 0 and 1 can be modelled as an infinite sequence of probabilistic trials. He achieves this by considering the number's representation in a given base, for instance, its decimal expansion. The choice of the first digit after the decimal point is one trial, the choice of the second digit is another, and so on ad infinitum. He implicitly defines a probability measure on the unit interval that corresponds to its geometric length. The probability that a chosen number will lie within a specific subinterval is stated to be the length of that subinterval. This claim ingeniously connects the geometric concept of measure with a probabilistic framework. His evaluation of the mechanism involves assuming that each digit in the expansion is chosen independently and uniformly from the available set of digits. For base 10, any digit from 0 to 9 has a probability of 1/10 of being selected at any position in the sequence. In doing so, Borel effectively constructs the Lebesgue measure on the unit interval through a probabilistic lens, years before its full formalization became standard. An assessment of this section's argument reveals its cleverness and its power. It provides a formal way to ask probabilistic questions about the properties of a real number, by translating those properties into statements about the outcomes of an infinite sequence of random digit selections. The coherence of this model is paramount, as it forms the bridge between the probabilistic machinery he has developed and the arithmetical questions he wishes to. Section 4. The central arithmetical application. The definition and existence of normal numbers. With the probabilistic framework established, Borel introduces the specific arithmetical property that serves as the paper's primary application, the concept of a normal number. His claim here is twofold, involving both definition and the statement of existence. First, he defines a number as being simply normal in a given integer base b if every digit in its base b expansion appears with a limiting frequency of 1 divided by b. He then extends this to the definition of an absolutely normal number, a far stronger condition, stating that a number is absolutely normal if it is simply normal in every integer base greater than or equal to 2. This act of definition is itself a significant contribution, isolating a specific property of real numbers that captures an intuitive notion of randomness in their digit sequences. The second, more profound, claim of this section is that such numbers exist. Furthermore, he asserts that this property of normality is typical for a real number. An evaluation of this part of the argument shows that it sets the stage for the paper's main theorem. Borel is moving from discussing probabilities to discussing the inherent, deterministic properties of numbers. The claim that normality is a widespread feature of the real number line is a startling one, as it suggests a deep structural order masquerading as randomness, or perhaps a randomness that is itself a form of order. The mechanism is one of precise mathematical definition, creating a clear target for the probabilistic tools he has assembled. The conceptual clarity of the definition of normality is what makes the subsequent proof possible and its conclusion so impactful. Section 5. The main theorem, the proof that almost all real numbers are normal. This section contains the intellectual climax of Borel's paper. Here, he brings his entire apparatus to bear on the concept of normal numbers to prove his most famous claim: the set of real numbers that are not normal has a measure of 0. Put another way, almost every real number is absolutely normal. The internal logic of his proof is a masterful application of the criterion he established earlier. For any given base b, he considers the set of numbers that fail to be simply normal in that base. He treats the deviation of the frequency of a particular digit from its expected value of 1 over b as a probabilistic event using principles related to the law of large numbers. He demonstrates that the probability of a significant deviation occurring diminishes rapidly as the number of digits considered increases. He then applies the Borel-Cantelli lemma, the sequence of probabilities associated with failing the normality test at ever-increasing scales forms a convergent series. Therefore, the probability that a number will persistently fail the test and thus be non-normal is 0. The set of non-normal numbers in base B is a set of measure 0. The final step of his argument is to observe that a countable union of sets of measure 0 is itself a set of measure 0, since the set of all non-normal numbers is the union of the sets of numbers that are non-normal in base 2, base 3, base 4, and so on. This entire collection has measure 0. An evaluation of this claim reveals its breathtaking scope. Borel uses a probabilistic argument, a logic of uncertainty, to arrive at a conclusion of profound certainty about the structure of the real number continuum. The proof's mechanism is a beautiful example of indirect reasoning, proving a property is universal by showing that the set of exceptions is negligible to the point of irrelevance from the perspective of measure. Section 6 Philosophical Implications and the Nature of Mathematical Certainty. In the final part of his paper, Borel steps back to reflect on the nature of his own discovery, embedding a subtle philosophical claim within his mathematical treatise. He grapples with a peculiar paradox his work has created. He has proven that a property, absolute normality, is possessed by almost every number, it providing a single, concrete example of such a number was, at the time, an intractable problem. The numbers pi and the square root of 2 were suspected to be normal, but a proof was completely out of reach. Borel's claim is that this gap between an existence proof and a constructive proof is a fundamental feature of modern mathematics, particularly when dealing with the infinite. He suggests that the methods capable of demonstrating the existence of objects with certain properties for an entire class are of a different character than the methods required to exhibit a specific member of that class. An evaluation of this argument shows Borel as a thoughtful mathematician deeply aware of the epistemological consequences of his work. He is drawing a distinction between two types of mathematical knowledge: a global, structural understanding and a specific, constructive one. This claim was prophetic, anticipating decades of debate in the foundations of mathematics, particularly the tensions between classical and intuitionistic or constructive schools of thought. There is a touch of intellectual irony in his position. He has used the most powerful tools of infinitary reasoning to describe a property of the overwhelming majority of numbers, while simultaneously highlighting the limitations of those very tools to pinpoint one. This reflection elevates the paper from a purely technical achievement to a document of profound metamathematical insight, questioning what it truly means for a mathematical object to exist. In conclusion, the 1909 paper by Emile Borel is a tour de force of conceptual innovation and rigorous argumentation. The evaluation of its internal claims, section by section, demonstrates a coherent and powerful logical progression from his initial, bold axiomatic extension of probability to countable sets. Borel meticulously builds a theoretical apparatus of immense power. The introduction of the criterion now known as the Borel-Cantelli lemma provides the engine for his analysis, a tool capable of translating statements about infinite sums of probabilities into definitive conclusions about long-term behavior. His modeling of the unit interval as a probabilistic space is an act of brilliant synthesis, linking geometry, probability, and arithmetic into a single, cohesive framework. The application of this framework to prove that almost all real numbers are normal is the paper's crowning achievement, a result that permanently altered the mathematical understanding of the continuum. His final reflections on the philosophical gap between existence and construction reveal a thinker of remarkable depth, aware that his work was pushing the boundaries of mathematical meaning itself. The claims advanced in this paper are not merely correct, they are foundational, shaping the language and trajectory of measure theory, probability, and number theory for the century that followed. The work's enduring significance is a direct consequence of the robustness of its internal arguments, which together demonstrate the astonishing power of probabilistic reasoning to unveil the deep and deterministic structure of the mathematical universe.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.